Hello again, and welcome to another review session for your final exam in Calculus 3208, presented by CDLI. We're nearing the end now of Unit 7. This is our second to last session. So this chapter 4 is the section 4.2 that we're looking at here if you want to compare to your textbook. But we're talking about, we've already looked at how we use definite integrals to evaluate areas under curves. We want to see the relationship now. What happens if the curve is actually below the x-axis? Do we have a positive or a negative answer? Is it possible to have something called a negative area? Well, we're just going to sort of clarify a few of those issues here in this session today. So we're going to look at something that's more specifically called signed areas. So not areas with signatures on them, but areas with plus or minus signs. And then we're going to look at net signed areas, okay, and how they compare to definite integrals. So we do assign a positive or a negative sign, but areas, of course, and the area concept there, areas are positive things, right? They're absolute value positive things. But we do assign negative and positive signs to them to talk about the definite integrals that go along with them. So let's take a look. So here's a couple of examples. In fact, this is a function f of x and its counterpart over here g of x. And g of x is basically just a reflection of f of x over the x-axis. That's all it is. So they're pretty much the same thing, just one is upside down from the other, flipped directly over the x-axis. So if you think about it, the area that's trapped between f of x and the x-axis on the interval from 1 to 3 right here, if I just flip the whole thing over the x-axis, I would have exactly the same amount of area that's trapped in between g of x and the x-axis. So what this tells us is that the areas are the same. This area is equal to 4, and this area is equal to 4. They're exactly the same. But they're definite integrals on the interval from, and this should say positive 1 up to 3 for both of them, not negative, excuse me. So their definite integrals from 1 up to 3 are not the same. Because when the definite integral is to find an area that's below the x-axis, we do what we call signing the area. So this is a signed area, and we say that the integral from 1 up to 3 of g of x here would be negative a. So that definite integral has a value of negative 4. Okay? Whereas over here, this definite integral, because everything is nice and positive up above the x-axis, would have a value of positive 4. So the distinction here is the areas themselves are always positive, but the definite integrals will be positive or negative depending upon whether the area you're talking about is above or below the x-axis. Okay? Important distinction. What happens if I have a function that does kind of this little dip thing and then comes back up and does all kinds of dancing? So basically here we have a function that has both positive values on some intervals, negative values on others. What the heck is going to happen with its definite integral? Well, here's a way to break that down and look at it. We've got 3 different areas here, area 1, area 2, and area 3. Okay? And we can see that area 1 is going to be above the x-axis in the positive region. Area 2 is below the x-axis in the negative region, and area 3 is again above the x-axis. Now all 3 of these things are going to be positive numbers because they're areas. But the value of the definite integral from a all the way up to b, so from here all the way to there, if I take the definite integral, it's not going to count them all as positive. It's going to count the positive stuff, so the stuff above the x-axis, as positives as their signed areas. So both A1 and A3 here are going to be positive numbers, and A2, while it's a positive number, when I figure it out as part of my definite integral, the definite integral considers it to be a negative number. Okay? So that's a signed area. So when I put all that together, I have some positives and some negatives. That's what we call the net area. So the definite integral, the integral from a up to b, of f of x dx always computes net area, not total area. If we wanted total area, counting all the areas as what they really are, which is areas, and call them all positives, we're going to have to split things up and account for bits and pieces differently. Okay? So the definite integral will evaluate all the areas from one end to the other, but it'll assign the positive and negative signs by default. It's sort of just a consequence of the way the process of integration works, okay? Because really, when you think about it, these heights are below the x-axis. So if you think about a Riemann sum, each of those heights would be counted as a negative thing, okay? That's what's going on there. All right. Example 1, compute the definite integral. So we can do that. So ignore the graph for now. We're just going to compute the definite integral here and see what we get. So the integral from -2 up to +2 of x cubed minus 4x dx. Okay. So I'm just going to do the antiderivative bit first. So that's going to be x to the power of 4 over 4 minus 2x squared, because it's 4x squared all over 2. And I'm going to want to evaluate from -2 all the way up to +2. So I want to find the difference between what we get at -2 and what we get at +2. So what's that going to be? At +2, it's going to be 2 to the power 4 over 4 minus 2 times 2 squared. And then I have to subtract what it is at -2, which is minus 2 to the power 4 all over 4 minus 2 times -2 squared. Okay, now here's what I want you to notice. We can go through all the nuts and bolts of this, but I'm going to save us all the agony. These two expressions are identical in every way except for these negative signs inside those brackets. And both of those things are raised to even powers, which means the negative signs are going to become positive signs. So whatever answer I get here, I'm going to subtract exactly the same thing right here. So what we end up with is 0. Now we want to look at the graph. Okay. So the first region on that graph, that's the region inside here, this business, okay? That's above the x-axis. And it's not hard to believe, if we look carefully at this particular picture here, that the second region over there is identical to the first region. It's just been flipped over. So all this stuff that I'm sort of coloring green down here, that's identical to the stuff that was colored yellow, except it's been flipped over. So the areas of those two things are the same. But as far as the definite integral is concerned, from -2 up to +2, it would take this area and it would assign a positive number, and it would take this area down here and it would assign a negative number. So when it does that, and if they have the same magnitude, it all adds up to 0. So the definite integral from -2 to 2 for that function is the sum of its positive and negative signed areas, which is 0. Now let's look at part B. It says find the total area between that curve and the x-axis on that same interval. Now, the total area and just the definite integral are not going to be the same, because areas are not really negative things. So our total area here is going to be whatever this one is and whatever this one is without that negative business attached to it, and then we got to add them together. So we can do that lots of different ways. We know they're identical, so we can just find the area of the top one and then double it. That'd be fine. But let's work through the motions to make sure it works out okay here. So let's first of all find the integral from 0 up to 2 of the same thing, x cubed minus 4x dx. Okay. So the integral from 0 up to 2, we already found out what our antiderivative was. It was this, only we're now going to evaluate it from 0 to 2. So that's going to be x to the power 4 over 4 minus 2x squared from 0 to 2. So that's 2 to the power of 4 divided by 4 minus 2 times 2 squared. And then subtract, and I'm going to cheat a little bit here. I'm just going to say subtract 0, because both of these evaluated at 0 will be 0, won't they? So let's allow ourselves to cheat a little bit there. So then what that's going to give us is 2 to the power of 4 is 16 over 4, which is 4. Subtract 2 times 2 times 2, which is 8. Okay, something fishy there. Wait a minute. Okay, no, that's fine. So that gives us an answer of -4. So that's actually this second area first, isn't it? Because I went from 0 to 2. Yeah, right. So that one gives us an antiderivative, or the antiderivative gives us a definite integral that works out to be -4. So I know that the actual area here, A2, is going to be a +4. Now let's evaluate to see what A1 is. So for A1, I want the definite integral from -2 up to 0 of the same thing. So if I do that, what I've got is, let's see, x to the power 4 over 4 minus 2x squared, going from -2 up to 0. So I'm going to cheat and say the first one is going to be 0 because they both have x's in them, so they're both going to make 0 there. And then I have to subtract what I get when I evaluate it -2. So that's going to be -2 to to the power of 4 divided by 4. Subtract 2 times -2 squared. And that turns out to be equal to +4. So A1 is also 4. So the answer here, find the total area, the actual total area, we'll call it AT for total, is 8. So the total area that's trapped between that curve and the x-axis is 8, despite the fact that the definite integral has a value of 0. And those are important distinctions, so I want to make sure we got that clear. Let's try and figure out this next example. I like this one, it's fun. This is actually a graph of y equals sine of pi x, but we don't really care about that today, I suppose. But I've got a graph of y equals sine of pi x here. And it says, on this graph, all of the areas, each of the regions, A, B, C, D, and E, that we have labeled here, all of those regions have an area of 1 unit. And it says to determine each of the following things. So what's the integral from 0 up to 1 of f of x? Okay, so let's see if we can figure that out. The integral from 0 to 1 of f of x is the region C. And remember, the integral will take account for the signed areas, but this one's positive anyway, so it's just going to be 1. Well, that wasn't much fun. Let's do the next one. From -1 up to +2. So I'm going to go from -1 here all the way up to +2 over here. So I've got a -1 for B, plus I've got a +1 for C, and a -1 for D, so that definite integral has a value of -1. Okay, let's look at the next one now. The next one tells us we want to evaluate the definite integral of our function from -2 up to +1. So from -2 up to +1. I'm going to go from -2 all the way over here, all the way up to +1. So I've got to take area A, which is a 1, area B, which is a -1. Well, it's a positive area, but we know the definite integral will be negative, plus area C, which gives us another +1. So we have an overall net area of 1. So we find that net area. Okay, for the last one, from -3 up to +2. Sorry, -2 up to +3. Reading, the ability to read would be helpful. Okay, so let's start from -2 and go all the way up to +3. So that's from one end to the other. So let's see. I've got 1, 2, 3 positive ones and 2 negative ones, giving me a net area for that of +1. Now we have to find the total area in part 5 between the curve and the x-axis. And remember, if we're looking for total area, then the definite integral will lie to us because it'll count certain areas as negative, which they really aren't. So we've got 1, 2, 3, 4, 5 areas all equal to 1. So our total area there is 5. Okay, fun stuff. Let's take a look at what's coming down the pipe, and I believe it's the your turn question. Okay, so this one's a little bit similar to the first example that we did, except they haven't got that nice symmetry where the two areas are the same, so you actually have to go and compute them both. So it says the graph of f of x equals x cubed minus x squared minus 2x is shown here. Compute the integral from -1 up to +2 of f of x dx. So we're going to go from there all the way up. So you want the integral first, just the definite integral, and then we want to find the total area between the two. So be careful about how you do that. I'll jump to the solution. So here is the solution to the your turn question. So the graph of all that stuff, it says we computed here, we get -2.25 for that one, +35 over 12 for just the area, the total area between the two axes, or between the curve and the axis. All right, running into the ability to speak here, sorry about that. And let's summarize what we saw. So here's what we know. When a continuous function f of x takes on negative values on an interval from a to b, we have the integral from a up to b of f of x equals -a. Okay? That's when f of x takes on negative values. When a continuous function f of x takes on positive values on an interval from a to b, we have the integral from a to b is +a. And when a continuous function takes on both positive and negative values on the interval from a to b. We have the integral from a up to b, f of x dx equals what we call the net area. So the positives are positive signed areas, the negatives are negatives. Add them together, counting positives and negatives, and you get the net area, which is the sum of the positive and negative signed areas. Hopefully that was helpful for you. Hopefully your studying is going well. If you have any questions, throw them up online. Thanks a lot for listening.